Okay, so today we're moving on from electricity. So we did like electrostatics, we did all of the circuit stuff. Now we're going to move on to magnetism. So if you wonder how magnets work, that's what we're doing today, Parker. So finally we're getting to that topic. I think this is actually one of the more interesting things we talk about. We also are going to, I see you, hold on a second. We're also going to talk about what I think is a really important thing to understand about how a lot of technology right now works, because this has kind of been like a recent thing that we've been able to do this really well. That thing is called induction. We might talk about it tomorrow. It depends on how quickly I can go through this stuff today, because I'm going to be honest, at this point, I just want to race through all the content so that we can watch movies at the end of the year. So that's what I'm trying to get done here. Yes, Macy?
It's not really a question, it's just like a general statement. You're annoying. You can explain.
Oh. Wow. I'm glad that's documented.
Okay.
So I look forward to showing that video of your harassment to, like
The
Mrs.
police.
Wyatt. And, oh yeah, the police.
You
That actually
doing
is-
about that.
It's not clear and present danger, I'm pretty sure. It's just me having freedom of speech.
Harassment's a thing. It's not, doesn't matter much.
Did it hurt your feelings?
Yes, but that's not a bar for harassment.
Can we just move on to magnets, please?
Yeah.
Okay.
Let's do physics.
Alright. Okay, so let's talk about magnets. I'm going to go through this faster than I should because, obviously I'm trying to get it done. What's so funny back there? I like jokes.
Oh my god. What are we doing?
I don't know.
To yell.
Sorry. Okay, so
This recording's gonna stop.
here's what we're going to talk about. What I love about this is that, y'all aren't going to watch this video again for, another 2 months. And then you'll get to watch it and be like, wow, you remember when Lawson was a goober and he was considered
That's exactly what I'm gonna say that.
Anyways, alright, so this first presentation, we're going to talk about magnets and why they exist and what they are from several different perspectives, okay? After we've done that, we'll talk a little bit about the mathematical side of mathematical force and all this kind of stuff. Then we'll get to induction. I would love to do all three of those things today. I don't know if I'll have time, but that's kind of what I'm trying to do because that'll save us one day next week. Alright, so getting into what magnets are, reminder about electrostatics, right? So we had these this idea that charge is either attracted or repelled from other charge, right? That was the thing. So that's a fundamental thing about charge is that it interacts with other charges, and that's what all of electrostatics and circuits even was based around. We also had these nifty little diagrams for electric fields, right? They looked like this. Let's make sure I hit all these points here before we move on. So again, we talk about these in terms of fields. We say charges generate fields that other charges respond to. That's kind of how we discuss all these things. Are we cool with that? Okay. Well, when we talk about magnets, what we learn is that magnets are forces not due to things having charge, but having charge and moving. Okay, so it turns out that moving charges interact with other moving charges. Does that make sense? So if there's something that is like a charge that's stationary, it won't feel the effects of a magnetic force, but if it's moving, then it will. So the idea here is not that charge exerts a force on all other charge, it's that moving charges exert forces on all other moving charges. And again, we could use the same language as before. The way we'll communicate this, we'll say that, hey, this moving charge is creating a magnetic field that other moving charges will respond to, right? Same lingo. This means that a charge that's moving is actually going to produce two fields. It will produce an electric field because it has charge, and it'll produce a magnetic field because it's now moving and producing a magnetic field. In fact, it turns out these two things are totally intertwined and basically two sides of the same coin, which is why we end up, a lot of times people will say things like the electromagnetic force. That's because we actually can kind of lump these together. That's beyond the scope of this class though, I just like to mention it. Alright, so you can see this moving charge The blue is the electric field that it's producing, and you can see it's like the field is pointing away from it. The orange is the magnetic field that it's producing, and here's what I want you to notice, okay? The magnetic field is not pointing either towards or away from the charge. It's like forming a circle around the charge. That's one of the important things that we're going to learn about these, is that the fields that are produced through magnetic forces, they're not the same as electric fields. We'll have this thing called the right-hand rule, which will help us determine which direction they are, but basically the field will always be orthogonal to both the velocity and hold on. Let's just say that. Orthogonal to the velocity, because I'm forgetting the way to explain the other thing in a way that will make sense, so I'll save it for when we do the right-hand rule. So never mind. Back up. Anyways, all right. So this leads us to, I think, an important discussion about permanent magnets and how they work. So talking about why are some materials magnetic. So what I've just discussed is how we think about like a single charge. Now let's talk about how we talk about lots of charges. So let's just get all the stuff up here on there. So the idea with a permanent magnet is that within this material, I have different atoms, and those atoms have electrons that we could think of as orbiting around a nucleus, right? Well, in most materials, those that motion is totally random, like this one on the left. So notice there, all those different little pockets, the orientations are random. And so that means that all of those moving electrons, they're producing magnetic fields, but because they're randomly oriented, all those magnetic fields are canceling each other out. So that material has no net magnetic field. So for example, this nail here, it's got a bunch of electrons that are all orbiting around each other, and so each of those individual electrons is creating a magnetic field, but they're all randomly distributed, so they all cancel each other out. Does that make sense? What happens with an actual like permanent magnet like this is that those motions are organized, so that now they're all creating magnetic fields that instead of canceling each other out because they're randomly distributed, they're all pointing in the same direction, so they add together and create one big strong magnetic field. Does that make any sense? So that's what's happening with a permanent magnet, is that the electrons are aligned. So what's interesting then, I haven't tried this before, is that like this is a permanent magnet. If I connect this guy to it, you may be familiar with being able to do this thing where it's like, hey, now this nail is actually a magnet itself, and I don't know if this will work. It's not going to be strong enough. Like I can feel it trying, but it's not strong enough. Trying with this, I don't even know if that material is magnetic. Okay. Oh, nuts. All right, so look, if I take this nut, and I'm very careful about it, I can get it to actually stick and hang. Like it's not, maybe it's not quite strong enough. It's trying though. I don't know if you can tell, but it's like holding on for an instant.
Is it too heavy?
It's because the nail is 100 feet long.
No. What I'm trying to tell you is that the nail is a magnet. Like right now, the nail is a magnet. It's a weaker one than this one, but it is a magnet. It's not that the magnetic field is passing through it. It's that the nail itself is a magnet. And as proof of that, if I hold, whoops, I don't know what I just did. Oh, I locked my computer screen. Whoopsies. If I hold this nut the same distance away, there's no interaction at all. So what's happening is not that this is a magnet and it just so happens that it's what's interacting with the nut, it's just too far away. Like what's happening is this magnet has made the nail a magnet. That's what's happening. Does that make any sense? So other materials may have a property that they themselves are not magnets, but when exposed to a magnetic field, they become magnets. Does that make any sense?
Mm-hmm.
In fact, that is the property that makes magnets attracted to metals, or at least certain metals. It turns out those other metals are prone to being temporarily magnetized. I'm going to show you what I mean once I log back into my computer. Maybe I shouldn't try to do this from a distance, but I'm going to try. Yay! Alright, so when we look at those materials, what we can then do is we can say that what really is happening here is that, let me get all the points up, is that when I take this metal, that again, like we know that metals have fairly flexible electron movements, right? Well, what happens is when I expose this metal to a magnetic field, it actually causes the orbitals of those electrons inside this metal to shift, which makes them have organized motion themselves, which is why I'm saying it's literally making the nail a magnet. Does that make sense? Once this is exposed to this, those individual electrons shift a little bit, making this a magnet, albeit a fairly weak one, and then the two magnets are attracted to each other. So what's really happening when you take a magnet and put it up to a non-magnet is it's making this a magnet so that then they're attracted to each other. Does that make any sense at all? Okay. So if we look at classifying the different materials, we can classify them this way. The first is a ferromagnet. So if you hear the term ferromagnet, that's referring to what we normally just call a magnet, right? It itself has an organized an organized magnetic field, and that's good. Then you have paramagnets, and most metals are paramagnets. They are materials that if I expose it to a magnetic field, it itself will become a magnet, right? Then you have diamagnetic materials, and diamagnetic materials are materials that basically, they do the same thing, but they have this weird quirk where instead of making a magnetic field that is compatible with the other one, they actually make the opposite magnetic field. I don't have those materials with you, but imagine that like, instead of me bringing this up to it and these like being like, hey, we like each other because we're both magnets now, they were like, hey, we're both magnets now, but we don't like each other, so they repel. Does that make any sense? That would be a diamagnetic material. That looks something like this, where ferromagnetic material is already organized. So if I bring a magnet up to it, it doesn't change the organization. Notice this picture and this picture are essentially unchanged. Paramagnetic material is randomly distributed. Their little individual magnetic fields are all randomly distributed. But if I bring a magnet up to it, they take on a rough organization and themselves become magnets. Diamagnetic material are instead where when I bring a magnetic field up to it, they actually reverse and go the other way and make a counter magnetic field. Does that make any sense? Okay. All right, so you are probably familiar with, if I take two magnets and I have them interact with each other, that there's one end where they'll be attracted, right? But if I flip this magnet around, they'll be repelled, right? Like they don't want to touch each other now. Does that make sense? Mm-hmm. So when we look at magnets, it's important to understand that magnets always exist as dipoles. Okay? They always exist with different ends, if that makes any sense. This was not true of electricity, right? With electricity, we have monopoles, meaning that something is positive or it is negative. With magnets, they always exist with both opposites within one structure. Does that make sense? So every magnet has two ends, and we call them the north end and the south end. Those names come from the geographic north and south because one of the things that we first understood about magnetism was actually the Earth's magnetic field to make compasses. And so now we just kept that language, right? That there's a north end of the magnet, there's a south end of the magnet. And what you'll see is that the like ends don't want to be near each other, similar to charge. So like two norths, they don't want to be together. Two souths, they don't want to be together, but a north and south, they'll come into contact with each other. important to understand that the field lines for magnets, they basically exist because of this dipole thing, they exist in loops. So this magnet actually has a field that runs through the magnet and creates these loops like this. So when you draw magnetic fields, they will always be drawn in closed loops. Okay? You'll never like start it from one end and go out because there's always a loop. The reason for that is because of this whole dipole thing. Moving right along, whoops, I just talked about this, right? So we should be okay with that. So what happens then when you break a magnet? So I did this for somebody the other day, and I've got a ton of magnets precisely because I like to be able to do this and show it to you. So if I take a magnet, all right, so here's a magnet. Where did the magnet go? Let's just use one of these. No, that won't sell it. All right, so here's two magnets, right? These, oh, my shoe's untied. These have a little bit of a line etched in them, so you know which side is the North Pole, right? So here's the little line there. Here's a little line there. Those are both North Poles. They don't want to be near each other, right? But if I flip it around, now they do want to be near each other. Cool with that? So then what happens if I take a magnet and I break it? Am I going to get a north end and a south end? The answer is no, you get two magnets. You guys already saw this. Let me see if I can break this real quick. Alright, so there, I broke it. Now what I want you to see is, I'm going to take the unaltered magnet and a piece of this magnet, and what I want you to see is, there's the line that tells you this was the north end. Well, that end is still a north end, but now the other end is a south end. So when you break a magnet, you just get more magnets. Does that make any sense? Mm-hmm. That's it. That's all that happens. The reason for that is because, again, this comes down to that organization within the material, right? And I could take that organization that exists throughout the entire material, and all I'm basically doing is cutting it in half. So this end is still organized, and this end is still organized, and so they're both magnets with the same north and south ends as before, because they have the same organization inside them. Does that make any sense? Okay. Where did my clicker go? Alright, so there's what I just said. I'll let you look at that while I tie my shoe real quick. Alright. Okay, so let's talk about Earth's magnetic field for a minute. So, like I said, we kind of named these things for Earth's magnetic field because that was the first most useful thing we had for magnets. So basically the idea is that a compass is just a small magnet, right? That's all that it is. A compass is a small magnet. And so what a compass is doing is it's responding to the magnetic field of Earth, and it's aligning itself with that magnetic field. So if that's the case, what should Earth's magnetic field look like, right? This is a bit of a weird question, but which way does the north end of a magnet point geographically? It points north, right? So that may be weird to you, but that's actually would indicate to us that the north end must be attracted to a south pole, and so the North Pole is actually the South Pole. So the North Pole is actually a magnetic South Pole. The South Pole is actually a magnetic North Pole. If you think of the Earth as a giant magnet, the north end is a South Pole, the south end is a North Pole. Because we named the poles of magnets based on where they pointed geographically, right? So this end points north, that's the North Pole of a magnet. Well, if it's pointing north, it must be attracted to a magnetic South Pole. And so that means that the magnetic, like the geographic North Pole, is actually magnetically south.
So whatever it's attracted to is
Just for the.
The opposite. Yeah.
Not like in all of
So
it. It's just the way they made it.
that's not really much more than like a fun fact, but hey, that might help you win trivia one day, right? So like now if you go to trivia and they're like, hey, where's the magnetic North Pole? You can be like, it's down in Antarctica with the penguins, right?
I think that's what we
What's
do.
the other one?
Huh? What are you talking about?
What is even happening right now?
Yeah, what is on the North Pole?
A magnetic South Pole.
No, but what is,
Oh, it's just a bunch of ice up there.
okay.
Yeah.
Okay.
Like, my understanding is that Antarctica actually has land and ice. I think the North Pole is literally just ice. Like, I don't think there's actual land up there. But I don't know. That's not my area of expertise. Go talk to, like, who teaches geography around here? Ripley? Go talk to Ripley about that. She'll tell you. All right.
Human geography.
What does that even mean?
It's culture, not necessarily landmarks.
Sounds like a stupidly named course, but that's not my area of expertise. All right. Okay. So let's talk about. Listen, focus. Let's talk about electromagnets. So the last thing that you may have thought about, or maybe not, is that a wire that has a current running through it has charges moving through it, right? If there are charges moving through the wire, then it must produce a magnetic field. This is where the first thing I actually normally do is I have you guys do a whole interactive thing with magnets where you can kind of like figure some of this out on your own. So this lesson is normally like, hey, let's answer all the questions that you had while you were going through that. We didn't get to do that, obviously, because I'm leaving you and we don't have time. So, that's a convenient thing that a wire produces a magnetic field, because that means that if I can turn the current on or off through that wire, then I can turn the magnetic field on or off, and that turns out to be a really useful thing to be able to do, right? Like the doors to this school all use electromagnetic magnets to keep the door locked, right? And that's nice because that means when I come up and swipe my badge, I can tell a computer to turn the magnet off so that I can open the door. That's a convenient thing, right? That's a helpful thing to do. So let's talk about electromagnets for a minute. So all an electromagnet is doing is it is replicating the organization of that electron motion, but it's doing it by having all the electrons move one way down a line. But what I need for a magnet is I actually need not a line, I need loops. And so if I take that line and I keep rolling it in on itself, I get a loop where now all those electrons are moving in the same direction with those loops, and that gives me a nice, strong magnet. Something like that. Make sense? Generally then, the more current I have running through that, the stronger the magnetic field is going to be, and also the more loops that I have, the stronger the magnetic field. I should actually say it this way. It's actually like the more loops per linear inch of the magnet, the better. And now I have something that I can run current through, and I can also easily shut that current off and turn the magnet off, which is convenient. Make sense? Okay. You may be familiar with some magnets having an iron core in the middle. You may not. I know when I was y'all's age, I built an electromagnet at home because I thought that would be cool, and it was, and I had a lot of fun doing it. But one of the things that I saw on the internet was that I should actually take a bunch of nails and like shove nails in the core. And the reason why I want to do that is because nails, like iron, is paramagnetic. And so what happens is when it's in the middle there, it's exposed to a magnetic field, and then it generates its own magnetic field, which strengthens the overall magnetic field that you're getting there. And because it's paramagnetic, when I shut that field off, it ceases to form its magnetic field and goes back to normal. So what you see a lot of the time with electromagnets is a coil of wire around a core of iron, and that's so that when I turn on the magnetic field, the iron magnetizes and I get a stronger magnet in the end. Does that make any sense? Mm-hmm. Okay. That's it. That's all I had for this lesson. So the intention of this lesson is to give you the basics of like what magnets are and how they work and all that kind of stuff. What questions do you have about that? Okay. What time am I done with y'all?